Hello and welcome to another WJEC A level physics question. This time is question 2 from June 2011's PH4 paper, and it's on simple harmonic motion. What we've got is a steel ball of mass 0.4 kilograms hanging from a spring. The ball is displaced vertically from the equilibrium position and then released, and a graph of the upward displacement against time is plotted using results from a video camera. And how can we tell that t is 0 is not the time when the ball is released? Well, if we look at the graph here, at t equals 0, the ball is actually in the equilibrium position, and we were told that the ball was released from some vertical displacement. So we're just going to say something like the ball is at the equilibrium position when t is 0. Next, we're going to write down values for the amplitude of the oscillation. So if we read carefully off the graph, we should be able to see that that amplitude is 0.08 meters. And the periodic time, the time for one complete oscillation, is 1.2 seconds. Next, we're asked to calculate the stiffness, the force per unit extension of the spring. Well, we're given the equation that t is equal to 2 pi root m over k. We're trying to find k, so I'll do a couple of steps here. First step would be to square both sides. So t squared will be 4 pi squared m over k. And finally, we can swap the positions of the k and the t squared to give k is equal to 4 pi squared m over t squared. So it's 4 pi squared times the mass was 0.4 kilograms. And we're dividing it by the period squared, 1.2 seconds. If we put those into the calculator, we will get 10.97 seconds, so it's near, sorry, not seconds, newtons per meter. So we're going to go for 11 newtons per meter. And remember that a spring constant is very commonly a unit mark question on an exam paper, so try to remember that k is measured in newtons per meter. Next, we're going to show that the maximum speed of the ball is approximately 0.4 meters per second. Well, formula for maximum velocity, not given in the data book, is Vmax is plus or minus omega A. Omega can be evaluated from 2 pi over t, so 2 pi over the 1.2 seconds. That gives us about 5.24. So now we can calculate Vmax as plus or minus. We're not too worried about that because we're just interested in the speed rather than the direction. So we've got 5.24 squared times that amplitude of 0.08, which gives us an answer of 0.42 meters per second. Next, we have to sketch a graph of velocity against time on the grid alongside, and we've got to plot the maximum and zero values carefully. Well, velocity will follow a similar oscillation to the displacement, in other words, it will have the same period. We've just worked out that the maximum velocity is near enough 0.4 meters per second. Now, if we look at the graph of displacement against time, we can see that this object at t equals 0 is moving upwards with a maximum gradient, and if you remember that the gradient of a displacement time graph is actually velocity, so at t equals 0 we've got a maximum velocity. That can also be derived from the fact that the graph for displacement against time is sinusoidal, and velocity is the rate of change of displacement. So if we were to differentiate a sine function, we actually end up with a cosine function. So our graph needs to be cosinusoidal, starting at about 0.42 seconds, and every 0.3 seconds, a quarter of that 1.2 second period, it goes from 0.4 to 0 to minus 0.4 to 0 and so on. I apologise about the quality of the curve, but it's not too easy to draw on this tablet. For part D1, we've got to calculate the changes in kinetic energy and gravitational potential energy of the ball between 0.6 and 0.9 seconds. And we've got to state whether each is an increase or decrease. So let's look at the kinetic energy first. Kinetic energy is half mv squared. At 0.6 seconds, the ball has a maximum negative velocity, and at 0.9 seconds, the ball has zero velocity. So it's going to lose all of its kinetic energy between 0.6 and 0.9 seconds. So the change in kinetic energy is going to be a half times the mass of 0.4 times the velocity of 0.42 roughly meters per second squared, take away 0. That will give us, 1 second, 0.035 joules. And this is a decrease, so we could call it a negative value if we like, but just so long as we make it clear. In terms of the gravitational potential energy, if we go back to the original graph, at 0.6 seconds the object was at its equilibrium position. At 0.9 seconds the object is 0.08 meters below that equilibrium position. So we can find the change of potential energy from mg delta h. So it's 0.4 for the mass, 9.81 for g, and delta h is 0.08 meters. And that one will give us an answer of 0.314. And again, that's a decrease. So this object seems to have lost both kinetic and gravitational potential energy. And the next part of the question asks us to explain, without further calculation, how the principle of conservation of energy applies over this period, over this interval. So basically, if we've lost both kinetic energy and gravitational potential energy, we must have gained something else. And that something else will be elastic potential energy. So what we're going to say here is something like the total loss of kinetic and gravitational potential energies will equal the gain in elastic potential energy. Just call it PE because I've run out of space there. Next, the spring is hung from with its suspended steel ball from the pin of a vibration generator, and this is connected to a signal generator so that the pin moves up and down. And using this apparatus, readings can be taken for a resonance curve, and we've got the curve on the right hand side. And we've got to label the graph axes for the physical quantities plotted. Well, this x-axis is the frequency of oscillation, and this y-axis is the amplitude of oscillation. We've got to determine the expected value of phi, which is explained in our reasoning. Well, phi is going to be the natural frequency. We get maximum amplitude oscillations resonance at the natural frequency of oscillation, when the frequency of the driving pin basically matches that of the spring there. We've earlier calculated the period, which was what, or we read the period off the graph, 1.2 seconds. So we can calculate that frequency by 1 over 1.2, which will give us 0.83 Hertz. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any questions. Goodbye.